And now I'm happy to introduce the last speaker of our session, Dr. Matt Reger, Senior Product Manager of Google Quantum. The focus of his research is on superconducting quantum computers. Matt earned a PhD on a prestigious IEEE Fellowship at Yale, where he developed the first millisecond time quantum memory for the superconducting qubits. His PRL paper, published in 2011 on this topic, was cited over 1,400 times. Matt published over 150 papers, which received over 7,000 citations. He was leading teams in the quantum computing industry for a decade. He was a principal investigator for DARPA, DOE, and USA Force quantum science programs. He was also co-founding PI and CTO of superconducting quantum materials and system centers. The US DOE Office of the Science, National Quantum Information Science Research Center, Director of Engineering and Vice President for Research and Development at Rigetti Quantum Center, Quantum Corporation. At Google Quantum, his team develops new algorithms and tools toward quantum advantage. Matt, thank you for joining us. And the floor is yours.
Is this coming through? Thank you, Olga, for that really kind introduction. It's humbling to participate in such an exciting moment here in Texas. As a Notre Dame grad, it's especially humbling to do this at Kyle Field after last week's football game. I'm going to take a step back a little bit and try to provide a bit of a roadmap for quantum computing as a whole. And we'll start by just appreciating how great computers are. This is how fast the fastest supercomputers are going. We can currently add 1 billion numbers together in a nanosecond. That's a lot of numbers. Do we even need more numbers? It's not obvious that quantum computers could ever outpace that. That's a lot of numbers. Moreover, we're in the middle of a revolution in artificial intelligence that promises to maybe even accelerate that trend, right? So do we need quantum computers in the first place? Obviously, we're having this summit because the answer is yes. There are problems out there that are truly intractable for any classical computing technology. So an example of this is that there is a bacteria that lives in the roots of bean plants that is responsible for producing a lot of ambient nitrogen fertilizer, right? In order for the agriculture industry to reproduce what that kind of amazing little bacteria does at kind of ambient conditions, we require about 2% of the world's global energy output, right? So if we can understand what this little bacteria is doing by using more advanced compute, then we could potentially unlock huge efficiency gains, for instance, in agriculture. This is the second quote that you'll see from Richard Feynman today. It's probably going to be two of many. Guys full of great quotes, but to paraphrase, if you want to understand things like how nature works at an atomic first principles level, you better use a quantum computer, damn it. Now, when we have, for the last 30 years and longer, been kind of unpacking the implications of that vision and rediscovering it in a lot of different ways, we've built a toolbox in theoretical physics to really compare head-to-head, apples to apples, with how quantum computers could potentially compute one day and how kind of abstract models of classical computers can perform in principle, right? And so what we've been able to identify as a community is something like 60 places where we have provable advantage between how quantum computation moves forward and how that would compare to a classical computer. So here's a few examples. We mentioned chemistry, factoring is another famous one. But the important takeaway is that there's a whole zoo. In fact, you can go to quantumalgorithmzoo.org and check them out. But it comes with an important caveat, and this is something that I think our team's been trying to make sure that people understand, is that while classical computers are still really good, when we try to lay out a quantum algorithm, it actually comes with an upfront cost of encoding that problem into these fragile quantum states that you heard Misha and June talk about earlier. So as an example, here's how we do a NAND gate in kind of transistor language, right? It takes a handful of transistors, it takes about a nanosecond. When we try to make the quantum version of a NAND gate, the picture is much more complicated. So there's something like a factor of 1 billion between some abstract notion of efficiency between classical computers and quantum computers. And so while you may have these provable asymptotic advantages between a quantum computer and a classical computer, that asymptotic advantage might not show up until really, really, really big problems that are likely to be not interesting or not computable, something like 10 to the 20 problem variables. So what that means is that in the hunt for quantum advantage for quantum computing, as a community, we need to be looking beyond the kind of vanilla Grover's kind of square root speedups. We need to be looking ideally at these kind of exponential use cases really quite rigorously. So you've heard already a number of really great talks about atoms. We're going to be hearing from almost all the modalities, I think, this week. So you'll be hearing a lot about all these different kinds of qubits. At Google, we're focused on designable circuits that allow us to rapidly iterate and learn and kind of improve these engineering integrated circuits. There's only 5 really hard things to do to make these kinds of quantum computers. We need to make better qubits. There's also the scalability challenge that we've heard already a lot about today. Something that our team is also kind of really pushing on is kind of combining advanced classical computing with quantum computing to do things like real-time error decoding. I'll tell you a little bit about that work later. After all these things work, the applications really need to be well understood and able to run. And we'll talk about cost someday. So here's a picture of a chip that the Google team has made. This is a picture of these so-called transmon qubits in an X shape, also known as XMON qubits. And what you see are kind of large patterned pieces of superconducting metal. Down here, you'll see maybe a couple pixels that represent the tunnel junction that allow us to take the superconducting circuit and make a qubit out of it. And there's some extra wires here to manipulate the circuit and measure it. These devices operate at very low temperatures. This is somewhat of an overhead, but they are commercially available systems. Here's a picture of our system when it's fully wired up. This is the kind of coldest temperature of a kind of multi-temperature stage system. Yeah, but to try to put this in perspective in a roadmap, I'll share our kind of mission statement, which is really to go after these truly unsolvable problems. What that looks like is a very long journey that's really focused on the basic science challenges that are underpinning quantum computing. So we've broken it out into these 6 milestones. The hardware gets progressively more abstract as we know less about it. We've recently checked off the first 2 milestones of this 6 milestone roadmap, and I'll be telling you about those in some detail. But roughly the way this goes is that we actually want to take on these state-of-the-art supercomputers right out the gate and really convince ourselves that there's some benchmark problem that quantum computers are actually good at. We're progressing now to this early quantum error correction regime that Misha told us a lot about. And next at Google, our main focus is building one very, very, very good qubit. From there, it's mostly scaling up and kind of running those large-scale applications. So about 6 years ago, the Google team introduced a processor that took a few hundred seconds, what actually took a few hundred years on the then state-of-the-art supercomputer Frontier. Let me tell you a little bit about the story of kind of what that algorithm is. We're going to take a click lower in terms of technical to maybe just tell you about this benchmark problem and kind of why we think it's an important yardstick for this kind of early quantum computing era. So we call this a beyond classical benchmark. And kind of time is moving from left to right here. Each of these boxes represent an instruction that we're programming into our quantum computer. And what we do is we create some pattern of these instructions that follow a pre-prescribed pattern where we choose at random some operation to perform to one of these individual qubits. And then we follow a pattern of entangling gates, right? So these are bringing qubits together, mixing up quantum information between them. As this algorithm unfolds in time, the entanglement actually builds up on the processor. As it does so, it creates a speckle pattern in the output that's actually exponentially hard for a classical computer to replicate. It's one of these kind of proven exponential speed-ups in principle. This benchmark was the first to show it in practice, where even accounting for finite errors, that as those cycles of programs build up, we're able to really kind of outpace supercomputers. Now, after this work was introduced, classical computers, in particular approximate algorithms for those supercomputers, actually continued to improve. A lot of it inspired by this challenge from the Google team, and kind of erased the speed up that the quantum computer was able to observe. In the meantime, we have not only been working on the classical kind of algorithms to replicate this machine, we've also been working to make better hardware. So up top, you'll see the kind of error performance of the then state-of-the-art processor in 2019. Over the last 6 years, we've been really focused on improving the quality of our qubits, improving the quality of the calibrations of these systems. We've been able to reduce those errors, in particular in these kind of fragile entangling gates, by close to a factor of 10. So what that means in practice is that as we scale the system up and we start to benchmark kind of chips at that kind of bleeding edge performance, they're twice as large as that original processor. What we find is that even using the kind of most advanced classical techniques that have emerged in that time period, when we do the comparison today, it's comparing something that takes a few minutes in Santa Barbara, California, would take 10 septillion years now on a supercomputer. So this is what we call our kind of Willow family of processors. Here's a lot of numbers about that processor that matter, I think, to the experts in the room. But just to point it out, these are not only state-of-the-art numbers for superconducting qubits, they also represent ongoing challenges and something that we'll be continuing to work on as a community indefinitely. In particular, things like the coherence time, which represent kind of how long these fragile quantum states can survive. We've very recently also been looking at the interplay between these early benchmarks for quantum computers and kind of places in the universe where the physics kind of resemble those benchmarks the most closely. We think that there might be kind of interesting areas of science to explore at the intersection, essentially, of chemistry and quantum information that relate to things like Hamiltonian learning. So, if we can parameterize these circuits and kind of learn about how information is spreading in physical systems. This also has fun parallels with black hole physics, as mentioned earlier. So, that was kind of the science and the progress that we've made behind this kind of milestone one benchmark. I'll give you, a little bit of explanation behind this this next milestone, which is really about making quantum error correction work for the first time next. Although my colleague Alec is going to be telling you kind of much more about this experiment this afternoon, so I will attempt to not do it justice here. The concept for error correction, as you heard from Misha, is to reduce the error of your operations by taking lots of physical qubits, encoding them into a quantum code analogous to how classical computers, classical communications work, right? So you need some redundancy in your system, and you need some way of checking whether or not an error has happened. We do that here by encoding multiple data qubits into a patch of what's called the surface code. So we need about d times d number of data qubits to encode one good logical qubit. And we think this is really quite needed to get to these limits of kind of provable quantum advantage, which, as far as we understand, needs kind of millions of operations. So this resulted last year in one of these data sets that, after working on this problem for 15 years, makes you think, oh, maybe this might work. maybe quantum computers might be possible. Which is that as we grow the size of this code, when the hardware is operating below what's called a threshold, as we add more and more redundancy to the system, the error rate actually drops pretty precipitously. And so there's this really beautiful white space in this plot, which is kind of quantum error correction at work. So each of these curves represent more and more data qubits participating in your logical qubit. This is the error rate. And so we see this really kind of steep roll-off where the kind of effective logical qubit is really cooling off and behaving quite nicely. This follows this kind of predicted exponential suppression because the system is operating below this kind of surface code threshold. And we're kind of able to really kind of carefully compare that to our models. Alec will be telling you quite a lot about that later today. Yeah, so that's where we are for milestone 2. After 2 comes 3, but it's far from an incremental step. Our goals in the near term are to create a logical qubit which can perform about 1 million operations, which, if you remember that plot from a minute ago, is about 1,000 times kind of more performant than this really exciting result from last year. In fact, it doesn't even show up on this plot. You would need the animation to undo it. So, when we kind of first did kind of potentially below threshold experiment a few years ago, we saw some suppression. Last year we saw kind of quite a lot of reduction in error rate as we grew the system size. In order to do this milestone 3 experiment, we're counting on not only significant advances in performance, but also pushing the scale out quite far. I think the thing that really wanted to make sure that we touched on is what these things are going to be used for. When we look at kind of what experiments people have been able to program onto the machine today, we know that kind of random circuit sampling, which has been performed now through multiple modalities, represents a very, very hard classical problem. At the same time, there's been interesting kind of physics demonstrations that are probably tractable, increasingly looking like something that people might care about. There's this big box of potentially real-world applications that are going to matter to people, not because it's a quantum computer, but because the answer matters. And what's been kind of giving us a lot of hope and a lot of learnings along the way have been these kind of impactful kind of research findings, where users are running on Google hardware and kind of learning something about the natural world through this kind of close collaboration with quantum hardware. Well, all of these are possible with high-performance supercomputers. A lot of it was enabled by this kind of close collaboration with kind of quantum hardware. Not quite full-on discoveries today. The team lovingly refers to these as discoverinos. In order to kind of get to these kind of larger scale applications, the Google team has a number of partnerships with kind of leading industry groups that are kind of teaching us about these kind of real world problems. I'll give you a couple of highlights as we close out. We opened this talk by talking about this little bacteria. At the heart of this bacteria is a cluster called FOMOCO. And it's one of the most widely studied quantum algorithms to date, both because it's very clearly classically intractable due to these heavy metal atoms, and it's also just a clearly important problem. When the first resource analysis was done for this system, it showed that a quantum computer might take a century, even a good quantum computer might take a century to understand this, right? So this is this kind of overhead showing up again. The good news is that over the years of really kind of understanding quantum algorithms in detail, we've been able to drive those resource estimates down from a century to maybe a few hours, right? So this is, you're seeing kind of incredible progress, not only in the hardware, but also in the kind of the computing primitives that kind of underlie these quantum speedups, right? So in this paper, we kind of showed some tricks for amplifying low-lying states in the encoding, and really kind of took another chunk out of this molecule. These trends are consistent pretty much across applications in quantum computing. One of the most well-known is Shor's factoring algorithm. When we look at the extent to which these techniques carry over to that algorithm, we find that yes, they do kind of one-to-one kind of accelerate the horizon of quantum breaking encryption. So post-quantum cryptography is very important, something that we're really focused on. Again, I won't extrapolate from this line, but we don't see any fundamental limits to continuing improvements within quantum algorithms writ large, right? So again, early days, prediction is maybe a billion qubits are needed. Today, the prediction is maybe about 1 million qubits might be needed to crack RSA. All of the work in quantum algorithms isn't just about studying those two problems that everybody knows and loves. There's a ton of opportunity to really discover new application areas. I think it's really encouraging that there's such a broad interdisciplinary group here today. Something that our team has worked on with Sandia is actually applying some of those tricks from quantum chemistry that are pretty similar to things that material scientists know and love in the quantum limit, carrying those over to problems like fusion. So there's this kind of interesting problem in fusion where if you start fusion in the lab, you start with something at close to room temperature. Eventually, it has to become simulating a process that occurs naturally in the sun. In between, what happens? It turns out that it's something like the interior of the Earth's core, and there's some really kind of meaty computational problems that we think quantum computers can actually tackle. And moreover, if you consider application areas that are already well understood within quantum computing, like optimization, there's still new concepts that are being brought to bear for those domains. So our team recently introduced a technique that we call decoded quantum interferometry that uses the quantum Fourier transform to map a hard optimization problem onto an easy classical decoding problem. And we think this is really just getting started. We have open source libraries that we encourage people to check out to accelerate this research. There's still a lot of work to do. Those problems are still there. And this is the last slide wrapping up Richard Feynman's quote, that wow, these problems are really hard, and they are. Thank you so much.